So, hey everyone, I'm going to go through a recent paper, a scientific report from Nature, which shows that experiments testing macroscopic quantum superpositions must be slow. So we'll proceed by first outlining a few of the background insights from standard quantum mechanics and special relativity needed to kind of make sense of the derivation in the first place. And then we'll contextualize the results by looking at some recent experiments demonstrating superpositions of microscopic or macroscopic systems. And then we'll go on to the thought experiment, which is outlined in the paper, as well as to two particular cases where we consider either test masses or test charges, and go through the derivation, which is ultimately a proof that any local experiment which discriminates between a coherent superposition and an incoherent statistical mixture requires a minimum time proportional either to the mass or the charge of the system. So first of all, I'm going to go through a bit of standard quantum mechanics just to make sure everyone understands the difference between a coherent superposition and a statistical mixture. And I think this is a really important difference. And this is what part of the proof subsequently relies on. So in the standard formulation of quantum mechanics, we use kets and bras to denote vectors and their duals. And they're represented in this sort of notation where you have a ket is usually represented like this, and this is just a vector in a particular vector space, and then its dual vector is represented by a bra, which looks like this. Then we consider the simplest example of a two-dimensional Hilbert space spanned by two qubit states. I will call these states L and R. And in reality, these states can be represented by a variety of physical systems, but for example, L and R could represent two orthogonal polarization modes of light, for example, left and right circularly polarized. So we have a Hilbert space spanned by two kets, L and R. And now we consider a simple example of a coherent superposition. So a coherent superposition would be written as a pure state, which, when properly normalized, reads something like this. So as you can see here, this is a coherent superposition where before we make a measurement, and whilst the state retains its coherence, it does not have a uniquely defined polarization in the left and right basis. However, we can determine the polarization of this particular state by making a measurement in the LR basis. And physically, this would correspond, for example, to detecting the state after it's passed through a polarizer, or in other systems, these measurements correspond to physically very different things. But that's not really important now. We just imagine that we make a measurement and then the state decoheres and loses its coherence. So we then project the state into one of the kets that comprises it, either L or R. So upon making a measurement, we get with 50% probability that the final state is equal to L. You can see. And with equal probability, the state decoheres into the right state. And therefore, upon making a measurement, the state loses its coherent properties. And this is somewhat counterintuitive and actually has been the subject of many years or many decades of debates amongst physicists. And it's also described as the measurement problem. And without going into too much mathematical detail, it is basically the absolute value squared of the coefficients of these individual kets, which give you the probability of making this particular measurement. So this is what comprises a pure state, and this is what happens upon measuring this pure state in the L and R basis. More mathematically, This state is pure because if we consider its density operator, which is represented in this particular way, so the density operator is the outer product, then the trace of rho squared is equal to 1 if and only if rho is pure. And for a state to be pure, it doesn't necessarily have to be in a coherent superposition. But importantly, mixed states are not pure because they do not satisfy this condition. And moreover, mixed states cannot actually be expressed as a single ket. So now to further outline the difference between a coherent superposition and a statistical mixture, I'll write down the density operator, which represents a particular statistical mixture. So I now consider sigma, which is a statistical mixture of the left and right states. And here you can see that I cannot express this as an outer product of a pure state because it's a mixture. It is the sum of two distinct components, and therefore it is fundamentally different from the coherent superposition state I showed before. And what is now a bit paradoxical is that if I perform a measurement on this non-pure statistical mixture in the LR basis, my measurement outcomes are exactly the same as for the coherent superposition state. And that is somewhat confusing because it would seem as if there is no way for me to distinguish between the two. So if I perform a measurement in the LNR basis, I get exactly the same. I get a 50% chance of measuring the L state, and I get a 50% chance of measuring the R state. And that is somewhat confusing. But there is a way to resolve this. So I can change my measurement basis, and I can now move away from the LR basis and consider a plus-minus basis, where my plus-minus basis states are again orthonormal, and they comprise of superpositions of L and R states with a different phase between the two states. And if I now perform a measurement in this particular basis, so I measure my coherent superposition state, which I then with 100% probability, I will get the plus outcome, because the plus state is literally phi. And if I measure my statistical mixture sigma, I get the same outcome as before. Probability of measuring plus minus. So the measurement outcomes are the measurement statistics are fundamentally different. And this is a particular example of how I would distinguish between a coherent superposition and a statistical mixture. And this is just one way. I mean, there are a variety of other interferometric experiments, and it depends precisely on the physical system that represents your qubits or your quantum states as to how I would perform this measurement. But this is just one example, and I think this is very similar to how the coherent superposition is represented in the proof later. But for a more comprehensive introduction, I'd recommend looking at Nielsen Chuang's Introduction to Quantum Communication, Information, and Computation. The next sort of intersection is on relativistic causality. So you can see here that I've restated the two principles that Einstein uses to derive special relativity in his 1905 paper on the electrodynamics of moving bodies. So the two principles are the relativity principle and the light principle. The relativity principle states the laws by which the states of physical systems undergo changes are independent of whether these changes of states are referred to one or the other of two coordinate systems moving relatively to each other in uniform translational motion. So that basically means that the laws of physics are the same in all inertial reference frames. The second is the light principle, which states that any ray of light moves in the stationary system of coordinates with a determined velocity c, whether the ray be emitted by a stationary or by a moving body. And that basically imposes an upper limit for the speed at which information can be transferred, which is given by c. And even though there's some controversy in 2011 about neutrinos which supposedly moved very fast, it turned out that these experimental results were wrong, even though they first announced that they measured particles with speeds greater than the speed of light. And no experiments have been performed which violate these principles. And therefore, and given the sort of theoretical soundness of Einstein's theory, it is a general desiderata for our other physical theories to be consistent with special relativity. And in particular, it's important to note, as you can see in this diagram, that light principle constrains the accessible regions of space-time. And in particular, the causal past and future, as you can see by these triangles here, is limited to a space-time region which is bounded by the light cone. So any of the regions which are denoted elsewhere here are generally inaccessible from the point where the axes intersect, because it would require sending information at speeds greater than c, whereas any of the regions inside the causal future or the causal past are accessible by signals which travel at speeds smaller than or equal to c. And obviously these dotted lines represent information transfer at c. And this is just a space-time diagram where we have x on the x-axis and time on the y-axis. And it was just important to briefly recap this, because this is actually the starting point of the derivation in that paper from 2016, where Mari et al. Show that experiments testing macroscopic quantum superpositions must be slow and are fundamentally bounded. I'll also give a quick recap of microscopic and macroscopic quantum superpositions. So demonstrations of microscopic superpositions are ubiquitous in experimental quantum physics. It was the entanglement of photons, which led to the Nobel Prize just very recently. And beyond that, there have been a lot of experimental demonstrations with coherent superpositions of electrons, neutrons, atoms, molecules, and many other sort of microscopic properties of matter. And this also, for example, forms the basis of building quantum computers, where some people are working with ion traps, some people are working with neutral atoms, and other people are working with photonic architectures or color centers, quantum dots, or even superconducting qubits. On the other hand, however, macroscopic superpositions, which go back historically to Schrödinger's famous thought experiment, where he considers a cat which is in a superposition of being dead and alive at the same time. They go back to the historical origins of quantum mechanics and have inspired a lot of lively debate. And in general, there's nothing actually that precludes standard quantum mechanics to be invalid at any particular length scale, but practically no such experiments have really been demonstrated. And the issue here is that as you increase the length scale of your experimental architectures and systems, decoherence, which is the loss of quantum coherence, where systems lose their quantum properties and they turn from coherent superpositions into mixed states, is a real problem for demonstrating any such superpositions. Because what happens is that usually the coherence time of systems is not particularly long, and especially if the systems become larger, they decohere very quickly because it's extremely hard to isolate them effectively from the environment, and any weak interaction with the environment destroys any sort of quantum properties, i.e. the initial coherence of the system irreversibly. But there have been some advances. The closest we've come is perhaps a recent experimental demonstration of a macroscopic superposition between a tardigrade, which is a small biological organism, and a superconducting qubit, and that sparked a lot of debate. And some people are also questioning the the validity of this result, but I think it's extremely interesting, as well as the entanglement of massive optomechanical systems. For example, in this paper, I show here, this manuscript will be released after the talk, by the way. People managed to entangle the mechanical modes of two mirrors. But let's move on for now and consider the starting point for the derivation in the Mari paper. So this is taken straight from the 2016 paper, and we consider a particular thought experiment. And this thought experiment is extremely idealized and doesn't really represent the real experiment, but it nevertheless is interesting and serves as a starting point for what will follow. So as you can see in this diagram, we have two particular laboratories. So we have Alice's laboratory and Bob's laboratory. They are spatially separated by a distance r, where r is pretty large. And in particular, R is much larger than D. So in Alice's laboratory, Alice has a mass MA. This could also be a charge QA, as we'll show later. The words mass and charge are very much interchangeable here. And Alice prepares a massive charge, or a massive or a charged particle in a macroscopic superposition of being either locally on the left or on the right. So these are these two positions which are described here. So Alice creates this local superposition where phi is in a coherent superposition of being either on the left-hand side of her laboratory or on the right-hand side. And the two positions are separated by a distance d, where d is much smaller than r. Then on the other hand, we have Bob's laboratory, where Bob has a test mass mb, and Bob prepares this test mass in a narrow harmonic trap. So basically, it's spatially confined in this trap, and therefore the mass mb is insensitive to any sort of interaction the mass experiences from the mass ma, because it's strongly confined in this harmonic trap. Now, Bob can send information to Alice by turning the detector off, i.e. removing the harmonic trap. And once Bob removes the harmonic trap, the mass mb and the mass ma experience interaction with each other because mass mb is no longer spatially confined. So Bob can either turn the detector off, in which case Alice would retain her local coherent superposition, or Bob can turn the detector on, i.e. remove the harmonic trap, and then after a time ta, after a time tb, the two masses or charges become entangled as they experience either a gravitational or electrostatic force. And Alice, in a time ta, makes a local measurement which allows her to distinguish between the coherent superposition or a statistical mixture, which is only present if Bob has turned his detector on, whereas she'll observe a coherent superposition if Bob's detector is off, i.e. if MB is still confined to this harmonic trap. No questions yet. Thus, if we consider these two timescales, so the timescale TB is a time required to generate entanglement between Alice and Bob's particles, the detector is turned on, and the time TA is required for Alice to make a local measurement that distinguishes between the coherent superposition and statistical mixture, and thus information is transferred in a time TA plus TB. And this, of course, as I said before, can be repeated for charged particles as well. So if we go through this more formally, as it's explained in the paper, we have Alice, who has a massive or charged particle in a macroscopic superposition of a left and right state. And in the position representation, these states will be represented like this, where D is the separation of the states, separation of the two states in superposition. And Bob is in a laboratory distance R away from Alice, where R is much larger than D. And Bob has a massive or charged test particle, and it's prepared in the ground state of a harmonic trap. And then Bob can either do nothing, which means the detector is off, or Bob can remove the trap, which means the detector is on. And in the first case, the test particle doesn't do anything and has no effect on MA, whereas in the second case, it is sensitive to the Newton or Coulomb field generated by mass MA. And so the coherent superposition, as I've explained before, is preserved if Bob's detector is off. But if Bob turns his detector on, then eventually these two particles interact such that the coherent superposition that Alice prepared locally is destroyed, and MA and MB become entangled. So the communication protocol would work as follows. There are two particular local states that Alice can measure, either statistical mixture or coherent superposition. So to recap and to make this consistent with my previous explanation, we have coherent superposition would be Alice can measure this state. And statistical mixture would be a state like this. In fact, this would be exactly the state that Alice would. Exactly the state that Alice would measure locally. And there's a direct correlation between detector off would correspond to this particular state, and detector on would correspond to Alice locally measuring the statistical mixture. Now, you may wonder how this measurement could be performed, because as I showed previously, if you measure this in the LR basis, you wouldn't actually find any difference between the measurement outcomes of these two initial states, which are fundamentally different. But as I explained before, she could, for example, project onto the L plus minus R basis, and then she would, for the coherent superposition, have a outcome which is always in the L plus R state. And for the statistical mixture, she would then detect with 50% probability, she would detect the L plus R, and with 50% she would detect the L minus R state. There are other ways to do this, for example, an interference experiment or a measurement of the velocity. And the details of the experiment are not of too much importance now, because the thought experiment is extremely idealized anyway. We're assuming that these two laboratories are perfectly isolated from the environment. The only interaction that is relevant is the interaction between the mass MA and B, or equivalently, if these are charged, the interaction between the charge QA and QB. And depending on the result of the measurement, Alice can deduce the choice of Bob. So as I said previously, just so this is really clear, if Alice measures a coherent superposition, then Bob's detector was off. And if Alice measures a statistical mixture, then Bob's detector was on. This is how they could communicate. And the issue now is that one may think that this would insinuate that Alice and Bob can communicate in such a way that Bob sends Alice one bit of information, as I've explained before, conditional on Alice's local measurement outcome. She can deduce whether Bob turned the detector on or off, which is the one bit of information that they can exchange. And it would seem as though if you make these masses large enough, or the charge is large enough, you can make TE plus TB, where TB is the time required for entanglement generation and TA is Alice's measurement time, arbitrarily small. And this would imply that you can send messages at a speed faster than the speed of light, which would violate relativistic causality, and you could somehow access regions which lie outside the light cone. And that is paradoxical, because we want quantum mechanics to be consistent with special relativity. And the authors in one present a variety of possible solutions to this, and we'll consider all of them. And I will partly follow their argument, but not into all the details. But basically, two of the solutions we can reject, and we will follow with the third proposed solution. So firstly, perhaps it's impossible to prepare such a macroscopic superposition or to preserve the coherence between the LNR states locally for Alice in the first place anyway. And perhaps standard quantum mechanics can't even adequately explain this result. This isn't particularly insightful, and as we'll see later, this is actually consistent with the much weaker and much more measured solution. But another option would be to say is that once Alice creates her local superposition, these individual states actually become entangled with their own electric or gravitational field, depending on whether we have charges or masses. And thus, her state from the outset is always mixed, which makes the measurement outcome independent of Bob's local operation anyway. So you can consider a situation where this state immediately decoheres because it starts interacting with its local electric or gravitational field. And therefore, there'll be no possibility of communication at all, and no superluminal signaling, because Alice's local measurement outcome is not correlated to whether Bob turns his detector on or off, because the measurement outcome is simply determined by the local interactions between the states and their electric or gravitational fields. A third and final option would be to require a minimum time for Alice to locally discriminate between the coherent superposition and the statistical mixture. And this is actually a bound that we can express. So we have TA and TB, as I've explained before, and then we can consider this to be greater than or equal to R over C, where R is the separation of the laboratories and C is the speed of light. And this would then make the result of the thought experiment consistent with relativistic causality. The authors prove pretty rigorously why the second solution I've just outlined is not a good one. And I would recommend my listeners to check out the proofs in more detail if they're really interested in the machinery. I'll just kind of try and summarize them and try and convey the main results. So firstly, one may think that a mass or charge is accelerated in the process of being placed into the coherent superposition, and that acceleration would lead to some entanglement with the emitted photons or gravitons. But it's shown in the paper that if these accelerations are sufficiently slow, then they can't even generate any photons or gravitons. There can't really be any local entanglement, which would collapse the superposition state in the first place and lead to its decoherence. Similarly, the particle can't really be entangled with its static Coulomb field, and that is related to the expectation value of the electric field depending on particle position, and locally the charge in the superposition of being either on the left or right hand side of the laboratory, and therefore this expectation value could be non-zero even if the modes of radiation are all in vacuum, and that doesn't really make any sense, and so there cannot consistently be entanglement between the charge's position and the Coulomb field. And again, I would refer the listener to the appendices in the Mari paper, because I don't want to go into this in too much detail, otherwise we're never going to finish and come to the final result. So this basically leaves us with the only viable option being this one, where we require some sort of minimum threshold for the time required for entanglement generation and for Alice to discriminate between the statistical mixture and the coherent superposition. And this is also actually consistent with the first proposal, because it allows for decoherence to happen before this time, in which case Alice can't make any useful measurements, and there's no inconsistency between the thought experiment, standard quantum mechanics, and relativistic causality. And now I will consider the two particular cases of a charge and a mass, and I'll go through the main results from the paper, and we'll rederive the bounds which are proven in the paper. One other thing that should maybe be noted here is that this obviously considers the sum of TB and TA, and we are really only interested in bounding TA. So we can sort of express this more subtly by saying that if entanglement generation happens in a time which is smaller than R over C, because of course if this is greater than R over C, then this bound is always satisfied, and we could sort of in infinitesimally small time discriminate locally between a coherent superposition and statistical mixture while still satisfying this bound. So what's really important is that if entanglement generation is sufficiently fast that it does not lie outside of this bound, then we require some sort of minimum time for the local measurement, and TA min is equal to R over C minus TA. And this again then expresses the minimum time required. So this would be a TB. Yeah, so now we will have a quick look at the derivation for a test mass. So bearing this in mind, because subsequently become important. I'll leave this one here for now. Yeah, so now we are trying to give a more precise estimate of this TA, not in terms of these quantities, which are generally unknown, but in terms of some other quantities which are more relevant to the system. So if Bob's detector is off initially, the mass remains stably trapped and its position is insensitive to the force exerted by Alice's mass. And this is kind of the uninteresting scenario because nothing happens to the Alice's local state. There is no decoherence, but the dynamics become interesting once Bob removes the trap, and then Bob's test mass experiences a force depending on the position of Alice's mass ma. And then we have two possible Hamiltonians, which are related to the local position of Alice's mass. So we have the Hamiltonian left and the Hamiltonian right. And they express so this is a position operator, this is the momentum operator, this is just a Hamiltonian, and MB describes Bob's test mass. So we now know that there's a force which is dependent on the position of Alice's particle, and we know that the spatial separation between the particles is d, so we can express the difference in force. Maybe take this off. We can express the difference in force as FL minus R is equal to G A MB D over R cubed, where R is the spatial separation of the laboratories. Now, since Bob has turned off the narrow harmonic trap, Bob needs to detect the position of Alice's particle, and that leads to the decoherence of Alice's local superposition state. And one can easily verify the presence of entanglement once Bob turns the trap off, because the two Hamiltonians expressed in equation 5, so these two, they lead to vastly different time evolutions. So if we initially describe the state of Bob's, so at time equals 0, MB is in state phi, and then we apply the time-dependent Schrödinger equation, and we convolve this initial state under a time t with the propagator given by the particular Hamiltonian, then we get two very different final states. So we can write the final state as, so this is the propagator, which is obtained by solving the time-dependent Schrödinger equation. So this would be minus h bar. So this would be R or L, applied to the initial state phi. This is at t equals 0. And then this is the time evolution t. And we can then see that the expectation value of these, projection of these two states is basically orthogonal. So they must be much smaller than 1. And this result is expressed in equation 7, where if you take the absolute value of so this is the bra, and then we have to take the complex conjugate, which is why the negative sign vanishes here. And the absolute value of this must be much smaller than 1. So this is phi final left, and this is phi final right. And we are taking the expectation value of these two particular states. So this is a bra, this is a cat, and these must be much, this result must be much smaller than 1 because they are almost orthogonal and their overlap is basically negligible. And it's instructive to consider the operator in between here. So this can basically be expanded by using something known as the Baker-Campbell-Hausdorff formula, which is just a pretty standard result from the theory of commutators and matrices. So I will use that now and just maybe for the audience, just recap this now. So Baker-Campbell-Hausdorff, where this is a standard result that e to the power of x, where x and y are possibly non-commutative matrices, is equal to e to the power of z, where z is also a matrix, and z is basically a particular expansion. I don't know if you see that. Yeah, z is an expansion, so it's plus y followed by a series of commutators. I will just write out it up to second order. You can verify this for yourself. But basically we can expand. So I don't know if you can see, this is up to second order, which allows us to expand this exponential term given here. So this can be expanded. So if we substitute in our expressions for HR and HL as given in equation 5, we can then expand this term, and the Loschmidt-Echo operator is given by 3 particular terms, which are linear in T, quadratic in T, and cubic in T. And we can neglect the term that's cubic in T, given that our time evolution is sufficiently short. And this then represents a phase-space displacement operator, which is well known. So we can express this in the following form. H bar, where this is delta x p minus delta p. And delta x in this case corresponds to delta f t squared over 2 mb, and delta p corresponds to minus delta f t. And then these are the shifts in position and momentum respectively. And we consider the initial state of the test mass to be in a very narrow harmonic trap. And given that the particle is spatially confined, we can invoke Heisenberg's uncertainty principle. So we know that the product of the uncertainty in position and momentum must be greater or equal to h bar over 4 pi. And this gives us some sort of bound on, if we know that the position is extremely well defined, we know that the uncertainty in momentum must be rather large. So if delta x is extremely small, delta p is rather large because we're dividing a small quantity by another extremely small quantity. And therefore, as argued in the appendix in the paper, I will just try and sort of reconstruct this proof as best I can. We consider an extremely deep trap, such that the harmonic trap is so deep that the mass on Bob's side is insensitive to the force exerted on it by the mass in Alice's laboratory. And therefore, a position measurement for Bob is always better than a momentum measurement, because this is extremely large. If this is extremely small, this must be large, and vice versa. And given that the particle is confined locally in a harmonic trap, this is always a worse measurement to perform. So a position measurement for Bob is always better than a momentum measurement, and therefore we consider the relative position shifts. So we have an expression for delta x, and we now consider this in comparison to the position uncertainty of the initial state, and consider the timescale TB, which is the timescale required for entanglement generation. So the important quantity we want to consider is this. Everyone can see this. So after at, so this will be approximately 1 upon entanglement generation. And that is because this is the initial uncertainty in position, and this is the phase space displacement. And once the phase space displacement is approximately equal to the initial position uncertainty, we know that the particles have become entangled because we're shifting the particle's position by a value which starts to exceed the initial uncertainty in position. And we know from this particular equation that this is equal to delta f t squared over 2 mb delta x. And delta x is the initial uncertainty in position, and one would maybe think that this would be arbitrarily small, but you can't reduce delta x arbitrarily because spatial localization is generally limited by something called the Planck length. So delta x is greater than or equal to Planck length, and therefore we can combine all these equations. So I'm gonna quickly delete some of this here. Delta x, the Planck scale. And therefore we can use equation 12, which is this one, substitute equation 6, which is a difference in force, and get an equation which is now expressed in terms of the values of the masses, the separation of the masses, as well as some other constants of the system. So we can rewrite this, since we know that delta F, as you can see here, is equal to G MAMB D over R cubed. We can now express this in terms of 1/2, and this should be an MB, by the way, sorry. 1/2 MA MP B. Oh, actually, no, it shouldn't. Sorry, this is some constant which is expressed as a ratio. P D C squared T A T over R cubed, which is still approximately equal to 1, because we're just substituting delta F into this equation over here. And T is also the time scale TB. So we obtain this equation from here by simply substituting in the value for the difference in force. And now we know that from our initial inequality, TA plus TB is greater than or equal to R over C, the only interesting regime which we are concerned with is if TB is smaller than R over C. Otherwise, there's no constraint on TA. So if we consider this particular, so TB smaller than R over C, we can then express TB in terms of a dimensionless parameter. So we say eta is equal to CTB over R, where eta greater than 0, smaller than 1, since TB is smaller than R over C. And we can use this equation and combine this with our previous equation, and then we get a particular bound on TA. So from the previous equation, we now substitute for TB squared over R cubed, and we obtain the result that, so this is equal to 1. So from this, we know that if we substitute in this result for eta, I'll create some more space here. If we use this result, then we substitute in eta cubed, then combining these two, we obtain the following. TB is equal to 1/2 eta cubed MA over MP T over C. So substitute in eta. So eta cubed is equal to C cubed TB cubed over R cubed. There's an additional factor of C and T beta, and therefore by multiplying everything by R cubed, and then substituting in eta, we go from here to here by substituting this into here. And again, using our bound, so we now have these two equations over here. And using this inequality, we obtain a bound on TA. So TA is greater than or equal to R over C minus TB. And substituting in this again is equal to, so R over C is equal to TB over eta, and this is just TB. So we then obtain, this can be rewritten as 1/2 MA over MP, where MP is actually the Planck mass related to the Planck length scale, D over C, eta squared minus eta cubed. Now, this particular quantity is just any, eta is just a dimensionless parameter of the system. So eta can actually take any values. We're not fundamentally bounded in what values eta can take. So we can perform just pretty simple convex optimization over eta. And optimizing over eta, we find a value of eta which minimizes this particular quantity. And plugging in that value of eta, we obtain that TA is greater or equal to 2/27 MA over MP D over C. And the important thing in this formula is that we have a time which is proportional to MA. So this is important and this is important. We have a time required for Alice to make a local measurement, which is greater than or equal to some numerical constants, which are not really relevant and kind of an artifact of this derivation. But importantly, they are proportional to Alice's local mass, as well as the distance between the two possible superposition states called left and right in this particular paper. And just by starting for a desire from, if we go back up, by starting for a desire for consistency with special relativity, and then doing nothing more but expressing two possible Hamiltonians for the local local gravitational field dynamics, HL and HI, we can perform a proof by evolving the system in time, applying the time-dependent Schrödinger equation, that using the inequality we wrote down before, TA must be greater than or equal to a quantity which is proportional to MA and D. So this is a proof that the measurement time required for Alice to distinguish between a coherent superposition and a statistical mixture is bounded by a time which is proportional to the mass MA, as well as a separation between the two local states. And in general, this result is expressed in the paper as follows. So given a particle of mass m prepared in a macroscopic superposition of two states separated by distance d, it is impossible to locally discriminate the coherent superposition from an incoherent mixture in a time less than up to a numerical constant. So as I said, the constant is actually not that important. It's the proportionality to the mass m, and there's two states separated by a distance d, and mp is a Planck mass. Now similarly, there are lots of other derivations in this paper for charges, but I will just repeat the derivation we had previously for a charge QA. So you can actually replace, as you can see in equation 21, you can replace the gravitational forces with an electrostatic Coulomb force. So now we go from equation 6 to equation 21, and we consider spatially separated charges QA and QB, which exert a static Coulomb force on each other. And the limit in equation 13 is now replaced by the charge particle radius. So here we had a limit on arbitrarily small localizations, which is limited by the Planck length. And here we have a limit on how small a charge we can actually discriminate. And we replace delta, we replace Planck length with the particle charge radius. So that would be QB over QP, where QP is the Planck charge. And then this is multiplied by a bunch of constants, as well as the mass mb. And then we can use exactly the same equations as we did in the previous derivation, and we can see that we're simply exchanging the ratio of the mass over the Planck mass by the ratio of the charge QB over the Planck charge. And we get exactly the same result. And one finds that the minimum time required for Alice to locally discriminate between a coherent superposition and a statistical mixture is proportional to her charge QA, as well as the spatial separation D between the two superposition states, which can be prepared, which are accessible in her laboratory. And so we have proven analogously to the case of test masses that the minimum time required for Alice to distinguish locally between a coherent superposition and a statistical mixture is bounded by a time proportional to the charge, as well as the separation between the two local states was given by D. And as I mentioned here, the curious reader can also check out two other derivations with respect to minimum time from entanglement with radiation, or the minimum time arising from quantum vacuum fluctuations. I decided to omit these proofs from our session because I think they would be maybe a bit too complicated, and they would take too much time because they involve slightly more advanced physics. But I think these proofs that I've shown here are actually extremely simple. All you need is to write down some sort of condition required for consistency with relativistic causality. Then you consider a particular Hamiltonian with two different components, one arising from the mass or charge being on the left-hand side and one arising from the mass or charge being on the right-hand side. Then you apply the Schrödinger equation, you evolve this system, you rewrite the operator here by using the big Campbell-Hausdorff formula, and then you get phase displacement, and then you make some sort of realistic considerations as to what the minimum uncertainty in position could be for a mass or a charge. And you bound this with the Planck length or the Planck mass or the Planck charge, depending on whether you have a mass or a charge. And then you obtain this pretty beautiful result. And the result using these other derivations will have a different numerical prefactor, but it still takes exactly the same form. So there is still a term which is proportional to the charge and the separation of the two local states. And just to finish off, I'll rehash how the authors express it here. So given a particle of charge Q prepared in a macroscopic quantum superposition of two states separated by distance d, it is impossible to locally discriminate the coherent superposition from an incoherent mixture in a time less than t is around q of qp, where qp is the Planck charge multiplied by d over c. And yeah, that's it. One of the maybe really interesting things is that they also think that this result is sort of analogous to Heisenberg's uncertainty principle, which is a pretty fundamental result, which makes quantum mechanics consistent with our other physical theories, and think that this could lead to more exciting experimental demonstrations with massive superpositions, and maybe also provide some insight on how this perhaps explains provide some sort of road to quantum gravity, and maybe provide indirect evidence for the existence of gravitational vacuum fluctuations, and perhaps also opens the door for possibly entangling a particle with quantum gravitational radiation. But yeah, that's it. If you have any questions, please put them in the chat. Oh, I've seen them. Cool. Is there any experimental evidence for electric or gravitational wave can entangle two charge or particles? How is the entanglement format? Bell state in some degrees of freedom. So when it comes to electric or gravitational wave, so I suspect you mean, yeah. So sorry, is there any So I think for the electric field, yes, there is. So for example, that's actually something the authors demonstrate later in the paper, that for a particular charge, you can consider the quantum vacuum fluctuations. And if you consider, I mean, this is not, you can't really consider this in standard quantum mechanics in the same way that you would, for example, consider a Bell state, but you would have to model the electric field as an additional Hilbert space, and then you consider the entanglement of the particle with the field. So you consider a tensor product of a particle Hilbert space and a field Hilbert space, and this is actually how the authors derived the bound using sort of a slightly different ansatz and using slightly more involved physics. And in general, for gravitational waves, I mean, there hasn't really been any sort of, especially not experimental, there hasn't, and not really theoretical either, there hasn't really been a demonstration of a quantum theory of gravity. I think this is something physicists are working very hard towards and would love to see, but there hasn't really been an experimental demonstration, and there's not even a sort of standard accepted theory for using gravity to entangle gravity as a kind of entanglement degree of freedom. I think this sort of is opening a whole box of worms with respect to making quantum mechanics consistent with some sort of theory of general relativity or some sort of quantum gravity, moving towards some sort of quantum gravity. But no, to answer the last part of your question, the entanglement formula is not like a Bell state. It's very for an, if you consider, for example, an electric field and a charge, then this is not simply represented as, for example, some sort of Bell state. So I hope that answers the question. Cool. Yeah, thanks a lot. Thanks everyone for tuning in. Hope you learned something, and yeah, have a good day. Thanks a lot.